All right, so in this video, we're going to talk about the binomial theorem. And the binomial theorem can find a specific term number's coefficient. So if you have a binomial to a certain power, you can definitely expand all that. And I'm going to kind of show you why we want to use this in just a moment. But I'm going to go through the theorem first, kind of show you what it looks like. But if you want to know a specific coefficient for maybe, the fifth or sixth term in this polynomial, once it's actually all multiplied out, then you can use this formula to find it, okay? So according to the binomial theorem, for a positive integer n and any real numbers a and b, we have the following. So you can see we have this binomial a plus b to the nth power equals, and we have this kind of complicated looking notation here. So it's c, we have a little n, we have a 0, and then you can see it's a to the n, which is by chance this n here, b to the 0, which we can see. Now we have cn to the 1, so now it's a, and it's n minus 1, and b has gone up to 1 from 0, so I'm taking 1 away from n, I'm adding 1 to b. So as I go up, you can see each one, I'm going to take the next one away from n for a, and I'm going to add give that to b. So hopefully you can see it building. I like to break this apart a little bit. I know it's probably not colorful on your paper, but I like to see it colorful on the page real quick because it just helps me see the pattern a little bit. So hopefully it helps you see it too. So I've broken it down. So here's each term, so you can kind of see them stacked. So you can see that the n, c, and then the number here is going down the term number, kind of an idea. So you can see a to the n, a n minus 1, a n minus 2, and we just keep going. We'll keep going with that until, if you notice, a goes down until it's 0. So it started at whatever exponent that we're starting with here on the outside, and it's going to keep subtracting until we get down to 0, until it's not there anymore. So our very first term is actually only going to have a in it, because if you notice, b is to the 0 power. Anything to the 0 power is 1. Right? Which means it's really not there because it's just going to be a to the nth power times 1. Same thing on the very last term. A is not going to be there, only b is going to be there. So we count down for the a for the first term, and we're counting up for the second term. So b is going up, and it's going to keep going up until it's at the exponent that we started with. So there's kind of this change off here. Okay, so this is it's a very specific pattern. It's not the easiest pattern to recognize, but there is a pattern happening here. Okay, so again, we start with no b and we end with no a. So the expression NCR can be evaluated for r equals 1, 2, 3, all the way to n, using the following formula. So I can use this formula to find a specific term number. Okay, so n with a factorial, r factorial times n minus r factorial. So this little exclamation point, if you already noticed, I'm calling it factorial. And this means that all the numbers up to this number will be multiplied. For example, 5 factorial means 5 times 4 times 2, 3 times 2 times 1. So if you notice, I took the 5 and I multiplied all the numbers before it, and I get 120. So that's what the exclamation means in math. It's factorial. So thus, each term of the expansion of a plus b to the nth power has this form. We can go the NCR, so this formula here, we need to know this number, times the first term to the n minus r, okay? So I do need to know what the r is. And then we can multiply b, or raise b to the r power as well. Okay, so where r is some integer from 0 to n. Okay, so it needs to be in between. It can't be a number less than 0. It can't be a number greater than n, because n is the exponent we're starting with. That's the largest exponent we can have. Okay, all right. So let's take a look at why. Let's think about why we use this formula, because it's not necessarily the easiest thing to look at. It is a bit complicated, but let's look at why this is actually easier to use than just multiplying. Okay, so if we look at 2z plus q to the 17th power, because this is the problem we're going to work this through on. And they want us to find what the coefficient for z to the third and q to the 14th power. So they want to know this specific coefficient. Well, if I look at the one expanded, here's 17 of them multiplied together. So I've expanded it. So that's a whole lot already. And what we're going to have to do to find a specific term number, we would have to multiply all 17 binomials, which definitely starts off easy, you know, because we can just multiply the first two, but it's going to quickly get very busy. So let's take a look at it really quick. So we have, oh, I forgot to unanimate those. We have 2z plus q times 2z plus q, just the first two. So that's not too bad. I end up with 4z squared plus 4zq plus q squared. So that's not too bad. Well, now let's take a look at multiplying the third one. We're going to multiply another one. So now if I multiply another one, now I have 8z cubed plus 8z squared q plus 2zq squared plus 4z squared q plus 4z q squared plus q cubed. And I can simplify that because I have a couple like terms in there. The 2zq squared and the 4zq squared are like terms. The 8z squared q and the 4z squared q are also like terms. So I can simplify that a little bit, but already we've gotten a little bit more complicated. Now, if I take that and I multiply again, so now I'm at the fourth step. Now look how long this has gotten. Look how many terms there are. And we're assuming, I checked this a few times, so I really hope I multiplied everything correctly. But if hopefully you're starting to notice there's a lot of room for error here. Once I start getting quite a few numbers, the more and more and more I multiply, the more room there are to make those little errors. And one little error is going to trickle down through the entire problem and is going to be very difficult to find going backwards. Okay, so if we look at the whole thing expanded, here it is. You know, we start with q to the 17th. We end on z to the 17th power. And our numbers definitely start to get very large here as we get through here. And if we look, this is actually the number we're looking for. We would do all that work, all that multiplication. That's a lot of multiplication going through there to get this number. We want that 5,440. Okay, so we know the answer already. That's actually the number we're looking for. But let's look at an easier way to do this. Instead of doing all this crazy multiplication and trying to multiply binomial after binomial after binomial, well, polynomial by binomial over and over and over again until we do that 17 times, let's look at an easier way to do this. Okay, so we're going to use that binomial theorem. So a plus b to the nth power. So let's plug in our binomial they gave us. It was 2z, that's our a, and q, that's our b, and n is 17. So I have those three pieces. So I already have the pieces I need in order to use the binomial theorem here. So n is 17. I don't have r, that's the one piece I need to find. 2z is my a. I do have n, which is 17, and I have b, which is q. So before I can fully complete this formula, I need to find r. So the task is to find the coefficient of z to the third, q to the 14th. So we'll use r equals, we want to make this 3, right? So what we're trying to do is I'm going to say, well, if I start with 17 and I want to go down to a number that gets me to 3, I'm going to subtract 14. And if I want this to be 14, well, that's also very easy. I'm going to make r 14, right? So basically, you just want to look at it and say, well, how do I get it to be where I want it to be? Because 17 minus 14 is 3, and 14 equals 14. So that gets me the exponents that I want. So that's how you decide what your r is. Okay. So now I have my whole piece set up here. So I'm going to go ahead and plug it all in. So here it is, all plugged in and nice and pretty. So now I have 17 minus 14, and that gets me 3, and then q to the 14th power. So here they are. Now I'm going to start to apply my pieces. So if you notice, this is just coming down. I'm not dealing with this quite yet. I'm going to have to deal with this in a moment because there's that extra little formula for this. So 2z to the third power, well, that's 2 to the third power and z to the third power. Don't forget to distribute that 3 to both. And then we have q to the 14th. Okay. Okay, so now we're going to take a look at the 17C14, okay? So we're going to deal with that because we need that number. That's actually going to be a number. So I'm going to use my factorial system here. I'm going to have 17 factorial and then 14 factorial times 17 minus 14 factorial. All right, so we're going to take a look at our calculator really quick. And you can see the 680 here, so I'm going to show you how we got the 680. So I'm going to go 17, and you should see a factorial button on your calculator. If you're on your phone, you may have to turn it sideways in order to see this. But you can see it's a very, very large number, okay? And then I'm going to go divided by, I'm going to use parentheses because I want to divide by 14 factorial times 3 factorial, so both. So I'm going to go 14 factorial, which is another very large number, times 3 factorial, which is not very big because it's just 3 times 2 times 1. And then I'll put the parentheses. So this is the entire denominator. And then I'm going to go equals. So that's how I got 680. So sometimes on your calculators, it's going to, let you see what you're typing in. On these, especially Apple products, they don't seem to let you see the history as you type it in. But make sure you're using, if you're, have more than one term in the bottom, that you're using a parenthesis. So it's 14 and the 3, not just dividing by the 14. So that is, how you use the factorial on the calculator. It is, in fact, on the calculators. And even the ones in class, we have them in the class, too. So now that we know this number, 680, we can put it here. Instead of that 17C14, we know that it's 680. So now I'm going to start to simplify these, and that 3 was getting cut off a little bit. It's 2 to the third power, which is 8. Remember, it's not 2 times 3, it's 2 times 2 times 2. Tells me how many times to multiply that 2. So I get 8, z to the third power, and then q to the 14th, just come down here. So now, all I have to do is this last bit of multiplication here. I have 5,540, which is that same number we already looked at, and then z to the third power, q to the 14th power. So it is still a bit of work to use the binomial theorem, but it's not as much work and not hopefully as much error as trying to actually multiply out 17 binomials. Okay, so that was the binomial theorem. I hope that helped, and I will see you on the next video.